So far, we've seen some properties of integrals that we can use sometimes for special classes of functions, like even and odd functions, or just rules about the limits of integration. We're now going to explore properties that work for all functions. That's important. It doesn't matter what the function f of x is here, these properties will be true. But we're going to change what happens inside the integral itself. For example, if we know the integral from a to b of some function is 10, then what happens if we put a 5 in here? And the short answer is exactly what you'd expect. But let's find for a rationale for this. Imagine if we had a function, here's our f of x, over some interval a to b. If we're told that the integral there with respect to x is 10, then we know what that area is. What we can do if we're asked to evaluate this integral is focus first on the integrand. This is like a new y value, which is equal to 5 times f of x. Well, that 5 is a vertical scaling. So if we went 1, 2, 3, 4, 5, we could resketch this graph as scaled 5 times in height what the original function was. Well, if that's the case, and knowing what we know about areas, I've kept the interval the same. It's still the interval over a to b, but now I've stretched things vertically by a factor of 5, and we're still going to go all the way down to the axis for this. We get the fairly intuitive result that we are going to have 5 times as much height, and if we have 5 times as much height over the same area, we're going to have an area of 50. To clarify the manipulations, though, what we're really saying is if we have an integral from a to b of some value times f of x, what we can do is bring constant multipliers out front and focus our attention on what's left inside the integral, exactly like you would have done with derivatives. If you took the derivative of 5 times some function, the 5 multiplier just scales your final value, your final answer. The same thing applies here for integrals. What if we then consider adding two functions, a function plus another function, and then find the area beneath them? Well, imagine we have an integral that is 2, has a value of 2, so let's keep this fairly simple. That's our f of x, and it has an area of 2 underneath it. And then we have our g of x on the same interval. That's the important part. That's the consistent part from example to example. Maybe it does this. Let's make it a bit taller. So it has an area of 4. These are the properties we've been given. A to B, A to B. And then we're asked, what's the area underneath the combined graph? Imagine this is a new y value. Well, how do we add graphs? We take the height at f and then we add the height at g, so we'd end up with something here around 3-ish. And then we would add those two graphs together. It's a little hard to sketch. We know roughly where we'd end up. It'd be up here. That combined graph on the interval a to b, you could actually subdivide it. You could say, here's the f part of it underneath. And then what we did is put the g on top of it, stack them vertically. And so unsurprisingly, when we have the integral of f of x plus g of x, all times these little widths delta x, we're going to get the area under f. That's this simple integral, wrapping it up with a dx. And then we can add the area under the g graph, like so. And we can just add them separately. In this case here, it would give us 2 plus 4 equals 6. So again, what we're doing is visually stacking one graph on top of the other graph, and then making a conclusion about the areas underneath them, which is what the integral is computing here. We've summarized these rules in the table here. Here's the multiplier out front. Key thing would be constant multipliers. And the second rule and third rule here are simply capturing the effect of having an addition of two complicated functions, f plus a g. you can integrate the f part first and then add the integral of the g part, and the same applies, of course, with subtraction. These tend to be quite intuitive for most students. Where we get into problems is with other operations like multiplication of functions. Those turn out to be complicated, but for constant multipliers or adding and subtracting functions, integrals behave exactly the way you would expect.